In this video, we'll prep for rational functions, specifically talking about the domain and how that relates to finding the vertical asymptotes for rational functions. Because you should have already talked about how to find the domain of rational functions, but let's talk about a couple of examples just to remind ourselves. So let's say if you're to find the domain of the following functions, or the first function, f of x, is equal to 2 over x minus 3. So this is rational functions where the denominator of the function is x minus 3. So the main thing is when you deal with fractions, remember, is that our denominator cannot be 0. So we cannot have values of x which will make our denominator 0. So one of the easiest things to do to find your domain for rational functions is, let's set our denominator, in this case the x minus 3, equal to 0, and then we solve that resulting equation, which this case is a pretty simple one. We just add 3 to both sides of the equation, so we get x equals to 3. So that would be the value of x that will make our denominator equal to 0. So one way you could write your domain is that you could say the domain is that x cannot be 3. We got to exclude any value, which will make our denominator equal to 0. Now, you may also be asked to write it in interval notation, which in this case would be, okay, so it could be any value except 3. So we would say it goes from negative infinity, but not including negative infinity. So remember, always put a parentheses on the negative infinity, comma, to 3, but not including the 3, and then union from 3, and again a parentheses on that 3 up to infinity. So that would be how you write it in interval notation. And now let's look at this other function, g of x, and let's find the domain of this one as well. So g of x equals to x squared minus x minus 6, all of that divided by x squared minus 9. Now, one thing I always find useful when we're dealing with rational functions, when not only finding the domain, not only finding the vertical asymptotes, is just to factor your numerator and denominator. Even though we only need to look at the denominator to find the domain, sometimes it's nice to, just while we're at it, to factor our numerator as well. In this case, x squared minus x minus 6, that would factor to x minus 3 times x plus 2. All of that all over x squared minus 9. If you remember, that's a difference of 2 squares because that's x squared minus 3 squared. So that factors to x minus 3 times x plus 3. So if we were just finding the domain of this rational function, like I was saying before, we would set our denominator equal to 0, and in this case we have it factored, so we'd have that quantity x minus 3 times the quantity x plus 3 equal to 0. And remember, by the zero product property, that if we have one thing times another equal to 0, then either the first thing is equal to 0, so either the x minus 3 is 0, or the x plus 3, this other thing, is equal to 0. And then solving those, so we get x equals to 3, or x equals to negative 3. So again, for our domain, one way you could write it is, again, these are the values which would make our denominator equal to 0, so we got to exclude those values. So we'd say x cannot be negative 3 or 3. Or again, in interval notation, we'd go from negative infinity, and once again, always a parentheses on the plus or minus infinities, to negative 3, union from negative 3 to 3, union, and again, not including the negative 3 or 3, from 3 to infinity. So that would be the domain of these rational functions. Now let's look at the graphs of these so we can see how does the domain relate to the vertical asymptotes of these rational functions. So let me pull up the graph and let's look at the first one. Oops, wrong thing. So we want to pull up the graph. So here's the graph of the 2 over x minus 3. So in red is the graph of this rational function. And one thing you would see is that as we go from left to right, it's going down, and then as we get really, really close to positive 3, it drops down to further and further down, and looks like it'll keep going down to negative infinity. And if we were to approach it from the right-hand side, it shoots upwards as we get closer and closer to 3. So what happens is that the vertical line x equals to 3 is what is known as a vertical asymptote. And then how do we find these vertical asymptotes? Well, if you think about it, we already did, because we found what is the value which would make our denominator 0. And in this case, that's x equals to 3, and the equation of the vertical asymptote is also x equals to 3. Now, but you got to be careful of that, because looking at the graph of the second function, the g of x equals to x squared minus x minus 6 over x squared minus 9, if you remember, our domain was x could not be negative 3. So once again, you see we do have this vertical asymptote at x equals to negative 3, but we don't have a vertical asymptote at x equals to 9, even though it did make our denominator equal to 0. Now, what it turns out, let's see if I could get really close on it, that if you notice, though, that if you get to the point when x equals to 3, hopefully you can see this, it says that point is 3 comma undefined, because the y value is undefined, because what you would actually get in this case is if you plug in 3 into the numerator and denominator, you would get 0 over 0. So even though you can't see it on this graphing tool, there actually is what is known as a hole in this rational function. But again, when we're looking for our vertical asymptotes, it's going to be very similar to when we're finding the domain of the rational functions. And again, to find our domain of our rational functions is we find what values will make our denominator equal to 0, and then we exclude those values. Now, one thing that will be very important, obviously, is that you got to remember all of your techniques for factoring, and also it may come up that you may not be able to factor, but it's a quadratic, so you may have to use something like the quadratic formula as well.